Hey, everybody. Welcome to the May 2022 SJAA Astro Imaging meeting. Tonight we have Bill Tschumy talking to us. He's the co-author of SkySafari. He's going to be talking to us tonight about his new our Galaxy app that helps us better understand the Milky Way. So take it away, Bill.
Great. Thank you very much. Yes. So it's probably no longer a new app. I mean, I've had this out for 2 years now, almost, although it's gone through a couple incarnations. But anyway, the talk will be sort of my motivation for doing it and things like that. So let's just start the screen sharing. Okay. I want to start playing this video and share. Okay. Looks good. Well, anyway, thank you for having me here. Let me start by giving an overview of what I'll be talking about tonight. First, I want to talk about this little motivation, why I was interested in this project and have been interested in this kind of project for a long time. Mention how I got started in this, because it's a moderately interesting story, I think. Then go through a few basic facts about our Milky Way galaxy. And some of this will be familiar to you, some of it won't be familiar. So hopefully everybody will get a chance to learn something. I want to talk a bit about the galactic coordinate system. Probably not everybody's familiar with it, but it's fairly important for understanding, how this app works and how to think about where things are in the galaxy. And then I'm going to pause my keynote presentation and I'll switch over to my iPad and run the Our Galaxy app there, because it seems like it works better for Zoom from my iPad for unknown reasons. And I'll demo the app and show you some things and teach you a little bit about our galaxy using the application itself. And then I want to talk about Platos Cave allegory, which many of you may have heard of, but it's relevant here, I think. And then finally, some conclusions. And again, feel free to unmute yourself and ask a question as I go along if there's something that's not clear, or if I've made some horrible mistake or something like that. So, where is M13? I used to have an app that I wrote a long time ago called Where is M13? And it was about this same kind of concept about where are things in the galaxy? And a friend of mine talked me into naming the app Where is M13, because that was one of my favorite, globular clusters. And I always used it as this question of where is this thing in our galaxy? So we know where it is in the sky. It's up there in the keystone of Hercules. But where is that in the galaxy? Who knows? And is it even in the northern galactic hemisphere or the southern galactic hemisphere? And I guarantee you, because I've done this, if you ask, 100 people, maybe 5% might have a clue on it. And the rest of people say, I don't know where it is. They might know the distance to it and how far away it is, but they don't really know where it is in the galaxy. And so we've always heard that our galaxy is, this disk with the spiral arms, and then the globular clusters kind of hover around it, like a swarm of bees is the analogy always used. And so, one of those dots there might be M13. Well, which one is it? So how did we get started doing this or thinking about this problem? Back in 1996, I bought the book Binocular Astronomy by Craig Crossan and Will Tyrion, and read it. And I found it a fascinating book. It's way more than binocular astronomy. It has a whole lot of information that has nothing to do with binoculars. And I thought it was fascinating. And I got a quote here from one of the chapters called The Structure of Our Galaxy. And it says, because we lie on the inner edge of our spiral arm, when we look at the winter Milky Way, which is away from the interior of the galaxy, we're looking back into our own spiral arm, the Orion arm. This is confirmed by all the relatively nearby open clusters, associations, and emission nebulae in the constellations from Perseus to Canis Major. And so when I read that, I hadn't really thought about that stuff before, even though I've been doing amateur astronomy for, coming on 50 years or so. And I hadn't really thought too much about where these things really are and what part of the galaxy we're looking at when we are looking at objects. And I really got interested in this. And so I read his book, and this book has a fatal flaw. Well, it's not a fatal flaw, but it's a serious flaw. He doesn't have any illustrations. And so he'd describe these things, and there'd be no pictures to help you understand what he was saying. And so I found myself drawing little diagrams like this. And so I'd draw the arms and talk about where things were and this and that. And I had a whole series of these little pictures that I kind of sketched out as I was drawing things to help me understand what he was saying. And then I said, well, maybe I can do better than this. And it was around, it wasn't right after I read the book, but back around 2006 maybe, I got interested in this again, and I decided to maybe write an app. And I said, well, I'm a programmer. I can write an app that will help show this stuff. And so I wrote this thing called Where is M13? And this is what the user interface looked like. It was written in Java. And so it was cross-platform by virtue of being in Java. And this is what it looked like. Nowadays, I look at this and it looks pretty crude. But back then, I thought it was pretty cool. And basically, it showed just a face-on and an edge-on view of the galaxy with the objects plotted on the screen. And it's kind of like an architect uses, two views of a building to kind of, see it from the top and from the side. And so I did that, and I plot these things, and I found it pretty fascinating. And I sold this for a number of years until I got involved in some other projects. So that's Where's M13. When I started doing SkySafari, after a couple of years in SkySafari, we were looking around for features to put in SkySafari. And I said, well, maybe I can use do something kind of like Where's M13. So when you select an object in SkySafari, you can say, well, show this to me in the galaxy view. And again, it would do the same thing. It would have an edge on and a face on view and where the object is. And so here, where M13 is labeled here, and you can sort of see where it is. So it's up above in the northern galactic hemisphere. And if you look at the left-hand side, it's kind of floating above our spiral arm as it winds into the galaxy. So when I left simulation curriculum, I said, well, maybe I can take this up a notch and do something else even more cool. And so these were my goals for this app that became our galaxy. I wanted to take the concepts that I used in Where's M13 and the galaxy view to the next level. I also wanted to incorporate instructional material to teach about the galaxy and the objects within it. And here is just a static shot of the user interface of our galaxy here. And as I'll show you in a few minutes, you can pan around in this view and look at it from different angles and things like that.
Hey, Bill, can I ask a question?
You can.
So what about velocity? Are the velocities known? Like, is everything, you know what I mean? Like, does everything go in the same direction, or M13?
No, not necessarily. And maybe so as I'll talk about, the stars in what's known as the thin disk all move in the same direction in more or less circular orbits around the core of the galaxy. There's something called the thick disk. And again, I'll show you this when we do our visualizations, where stars are not moving in circular orbits, and they move up and down around the plane of the galaxy. There are some star streams that appear to be captured from other galaxies that are coming in at weird angles and orbit in non-expected ways around the galaxy and things like that. And of course, the globular clusters themselves are not in the plane. But I can hopefully talk about that a little bit more as we go on in this. So at this point, I want to mention a few basic facts about our Milky Way galaxy. So the image I use in everything from Where's M13 to the galaxy view to our galaxy is this. And this was an artist rendering based upon data from the Spitzer Space Telescope. And it took that data, and the artist made its best guess as to what our galaxy looks like. And of course, we we can't get a camera up above the plane of the galaxy and look down and see what it really looks like. And we've barely got anything out of our solar system. So we certainly can't get up here outside the plane of the galaxy. But this is what they sort of thought it was. And I'll also mention at this point that, we really only know what's going on in this sort of region of the galaxy here. Over on the other side from the galactic core, we know very little about that. Infrared telescopes that look back in infrared, they can sort of see through some of the dust and kind of figure out a little bit about that. And we're now learning more about it, but this is kind of very speculative, even more speculative on the other side of our galactic core than it is on our side. Oh, I should mention that little orange dot there is where the sun is. Of course, it's drawn many, many times bigger than what it really is, just so you don't have to have a microscope to see it. So our galaxy is around 100,000 light years in diameter. Some books will say 150,000, some books will say 80,000. It's not a hard, there's not a hard line to the disk of our galaxy. I mean, it kind of fades out. And so the question is, well, where do you say it ends? And given that 100,000 light years is a nice round number, I just use that. And a lot of other people use that too. The distance between spiral arms is about 6,000 light years. So again, if you're in our, here by the sun, and you're looking at something that's in the next spiral arm outward, or if you're looking at some object out in this direction, and it's about 6,000 light years away, where you say, oh, that's probably in the next spiral arm outwards. And likewise, if it's about 12,000 light years away, it's probably in the arm out beyond that. And so you can kind of get a sense of what arm things lie in by its distance. There's a galactic bulge in the center. It's not spherical. It's a football shaped type thing, about 7,000 light years in that dimension, maybe 20,000 light years in that dimension there. And it's about 12,000 light years in thickness, if you look on an edge on. And then our arms, our disk of our galaxy, which is called the thin disk, is about 1,500, maybe 2,000 light years in thickness. Everybody got that? A few other facts. Our galaxy is believed to hold about 200 billion stars. The mass of our galaxy is uncertain, of course, but it's believed to be certainly greater than 1.5 trillion solar masses. And half of that mass is in stars and half of it is in dust and gas. The total luminosity of the galaxy is about 10 billion times that of the sun. Of course, we like to name things. So all these arms have names. We have the outer arm, our Perseus arm. This is our arm is called either the Orion spur, sometimes it's called the local arm. The next arm inward is called the Sagittarius arm, then the Scutum Centaurus arm, and then the Norma arm is the most inner one. Arm. So, any questions about that, or should I go into the galactic coordinate system? All right. So the galactic coordinate system. It was established only in 1958 by the International Astronomical Union. So it's a spherical coordinate system, and it uses our galactic plane as the equator. Galactic latitude is the angle above or below this plane. So this object here is sitting up above the plane of the galaxy, and its latitude is that angle there, labeled lat. Galactic longitude is measured along this line. So 0 galactic longitude is pointing toward the core of our galaxy. And then you measure around 90 degrees longitude is here. So if you're looking off in that direction, sort of down our own spiral arm, you're looking at 90 degrees longitude, 180 degrees longitude over here, and of course 270 over here. And then of course, the North Galactic Pole is at 90 degrees latitude and the South Galactic Pole is -90. And so it's kind of When I first came across this, I thought, well, it's not really a galactic coordinate system, because it really is, it's centered on the sun. It's not centered on the core of the galaxy, which is kind of what I might think it would be. But this, as it turns out, works out very useful like this. And of course, they do have another galactic coordinate system that is centered on our core. And of course, back then, they didn't really know, when they first established this, they didn't know exactly where the core was. And so it would be kind of silly to design a coordinate system where you didn't really know what the origin was. And here's just another diagram in case that first one didn't catch your eye or make it understanding. So latitude, again, is up along this spherical plane or spherical sphere, and longitude is around this thing. And again, the important thing to remember is 0 degrees longitude is toward the core of our galaxy. So you can plot all the stars or night sky in the galactic coordinate system. And when you do that, again, 0 degrees latitude is this red line going along here. So that's all things in the plane of our galaxy. And that's why you sort of see the Milky Way kind of in the background here. And again, north latitude and south latitude are above and below that red line. And of course, where the two red lines intersect is 0 latitude, 0 longitude, pointing at the core of our galaxy. So it's nice to, and again, this is a screenshot from our galaxy. It's nice to switch back and forth between the galactic view in our galaxy and this sky view to kind of get a sense of, how what you're seeing in the galaxy kind of meshes up with what you see in the night sky. So where's M13? There's an object info panel you can pop up, and I've highlighted the galactic longitude and latitude here. So again, the angle from the sun here up to here is about 41 degrees up here, and it's 59 degrees from the core of our galaxy on around to where that is. And the other thing that's kind of useful is what's the distance from the galactic plane, and so it's about 15,000 light years above our galactic plane. And of course, up here, the distance from Earth is about 23,000 light years. So again, what I like to say is, people are used to kind of, knowing the distance to objects, or at least they look up the distance to objects, and they find that pretty interesting. What I'm trying to do is to convince people that the other interesting thing is to look up what its galactic longitude and latitude is. And that, in conjunction with knowing the distance, you can figure out where it is in the galaxy, particularly if you have an app like this. Okay, so I'm going to switch screens, assuming this is going to work for me. I've been doing this presentation on my Mac. I'm going to stop screen sharing the Mac. I'm going to just start screen sharing here. And there you go. So this will look a little jerky, slightly jerky, depending on your internet speed and stuff as I pan around. But I'm touching the screen with my finger and kind of panning right now. So you can kind of do this. You can go like this and look at it from below. Things like that. Is that working for everybody? Anybody got a problem? You can see what I'm doing.
Looks good to me.
Okay. Well, let's assume we're good to go then. So it's a fairly simple user interface. As I say, there's this button in the center, the lower toolbar. There's Galaxy and Sky. The Galaxy is highlighted. If I click on Sky, that gives you that sky view. Right now, there's no objects other than the stars that are there just for reference. But this view doesn't have anything. The objects displayed in it. So on the left-hand side, this button here, which I'm going to tap on, brings up this sort of views menu. And as I mentioned, one of my goals was to have a bunch of educational material in the app. And so what I've done here is there's a bunch of built-in views. You can save your own custom views, but these are built-in views. And so One category is stars and OB associations, open clusters and whatnot. Tapping on that info thing, again, a little thing about stars and what's going on with stars. But if you drill down and tap on the stars itself, it'll show you some different views that I built up for showing the stars. So if you want to see all the stars, say that are in our app, and again, it's not, I have stars down to about 6.5 magnitude. There was, I mean, if you have stars to, 12th magnitude, the app will run so slow and it'll have so many stars, it'll just be, impossible. So here's the view. So what I've done here with this view is it turned on a set of axes showing where things are in the galactic coordinate system. So again, you see the one on to the right pointing to 0 degrees. So that's pointing back to the core of our galaxy. And if I pan around, sure enough, there's 0 degrees pointing back to our galactic core. 180 degrees, of course, is just the opposite. And I've labeled a few of the bright stars here, so you can kind of get a sense of where they are. And they're kind of, obviously it makes sense. I mean, think of Antares. Antares is in Scorpius. Scorpius is back, near the galactic core. And sure enough, if you go over here and look at it, it's going to be back near the core there. So you can see where your other stars are. And then Betelgeuse is 180 degrees away almost, looking out away from the core of our galaxy. Using the buttons, the plus and minus buttons along the toolbar there, you can zoom in. You can zoom out. If I zoom way out, so you'll see that all the bright stars in this thing, and when I'll just hide these axes for a second. All the bright stars are like a little pile of salt there near our sun. And if you think about it, that makes sense. Stars far away or dimmer. So all the bright stars you'd think would be very close. And so it's surprising. And I've got maybe 6,000 stars in the database, is all I decided to put in here. And so that's where the brightest 6,000 stars are in our galaxy. And there's a few way out here. If I tap on that one there, so New Cephei is off over here. I can tap on that little star there. 6 Cassiopeia. So there's stars fairly far away, but most of them are kind of piled in very close to our sun. If I go back to the stars menu, one of the things that I find kind of interesting is the constellations view. And so it's going to show you what the bright stars what the bright stars are in our galaxy, or excuse me, in a particular constellation. So let's choose one. Let's choose Auriga. So here are the stars of Auriga. And so they're all stretched out here to the left. Now, as you know, Auriga is more of a winter constellation. And so as you think, it's off pointing away from the core of our galaxy. So here you can see all the bright stars in Auriga there. And what I find kind of interesting is if you take this and zoom in on them, you might expect eventually you get where you can actually see the constellation. And as you get close to the sun, so the positioning is what you expect. So here's the bright stars of Auriga, kind of making a circle. And unfortunately, I can't point on my iPad to kind of, there's no cursor here I can use to outline them, but you can kind of see a circle of stars starting at Capella, then going up and to the left to Minkalion and on around, which are the stars of Auriga. So we'll zoom back out. And the other thing I'll mention, so let's actually just go here. I'll do stars, constellations. Let's do Cygnus, for example. So there are stars with Cygnus. So when you're looking at Cygnus, you're looking at stars that are kind of down our own spiral arm. If I zoom out, so here we are, we're on the inner edge of this spiral arm that's to the left of the center of the coordinates here. The stars kind of go off into the spiral arm as it curves back into the Milky Way, or the core of the Milky Way. Another good thing you can do, though, is if you go to this little hamburger menu over here on the right, under labels, you can say label the spiral arms. Excuse me, not show the constellation sectors what I want to do. So here we'll show you when you're looking at a particular constellation. And again, these are only constellations that intersect with the Milky Way up in the night sky. This is where you're looking in the galaxy. So Cygnus, again, this little wedge for Cygnus, you're looking down at that arm. See Auriga over there to the left. That's the one we were looking at previously, off in that direction. So this is a good way to sort of get a sense of, oh, I'm looking in this constellation. Where am I looking in the galaxy? What part of the galaxy am I looking at? By turning on these constellation sectors, you can see that. And I'm going to turn them back off right now. So those are the stars. I'm going to skip OB associations right now. OB associations are young groupings of hot O and B stars that have just recently formed. I mean, I can just briefly just show all OB associations. They tend to be in the spiral arms themselves because that's where star formation is happening. But these are all the major OB associations we know of in the galaxy and where they're located in the arms. I go to open clusters.
How come there are no OBs anywhere else in the galaxy?
Because it happens, well, they do. Again, it's the same thing at, let me zoom out. So all these are pretty close to the sun in the same way that the bright stars are close to the sun. I mean, there's surely OB associations, you know, in all the arms, in all the positions of the arms around our, you know, in the plane of the galaxy. We just can't see them because they're obscured by dust. But this is the main ones that we recognize right now.
So, for instance, the late, you know, the most recent Gaia data.
And I don't have that in there. Yes, the Gaia data. I've actually not seen new named OB associations based upon it, although surely probably people have done that or are doing that now. And I will comment that a lot of the objects I have in here are based upon the DR2 version of the Gaia data, the first release of Gaia data. They're now up to DR3. My goal here in not too long is to go back and some of the distances have changed to things. So I'll go back and redo the database using the DR3 release of Gaia data.
Bill, I
yes.
think up to DR9, I thought was the last release. But anyway.
9? No, that's DR3.
I know that's better than me. But that's the way I remember it.
Yeah, no, it's 3 is what they're up to.
Okay.
Pretty certain on that. Open clusters. So if we just want to see, let's show all the open clusters that are known. We get this. So again, we switch to an edge-on view here. But that's all the recognized open clusters that I was able to pull out of Simbad when I sort of harvested the data out of that. But again, if you pan, you can sort of see where they're oriented here. Again, sort of zoom in on them. And again, some of them, this guy over here, that's M24. It's not truly an open cluster, of course. But it's the closest thing we can call to an open cluster, I guess. Or open cluster is the closest category, I guess you can put it in. But it's a view of that arm through a hole in the dust, such that we can sort of see that into that inner arm there, and that's where M24 is. You know, other things, if you're going to just tap on these objects, you can see where the different clusters are. Colander here, NGC 61, 69. So again, you can kind of see where these are. And again, most of these are in the plane of the galaxy, or close to the plane of the galaxy, not exactly. You can actually, as many of you might know, when clusters form, they form in the plane. And as they age, they usually migrate out of the plane, or at least the ones that are out of the plane tend to be very old because they've sort of migrated out. And you can show that here. So if you do say young open clusters, and I think I defined young open clusters as things younger than 100 million years. Most of those are all really right in the dust lanes of our plane. If I go back and do it for old open clusters, you'll see there that there's quite a few of them, just they're no longer concentrated along the midline of our disk, but they've migrated off. And again, that's what things do. They form in the plane of the galaxy, and then as they get gravitationally disturbed by, other giant molecular clouds and things like that, they get disturbed and get sort of migrated off from the plane of our galaxy. Diffuse nebulae. This will show you where the nebula that you imagers love to photograph and things, like North American Nebula and Cygnus. Again, the red ones are emission, the blue ones are reflection, and there's some green ones in there that are both emission and reflection nebulae. But this will give you a sense of where these are. And again, these are all pretty much in the plane of the galaxy. Back out of it. So you really don't get nebulae off the plane of the galaxy. I mean, the nebula depend upon the dust and the gas that's in the spiral, the plane of the galaxy. So they're all going to be in there. I'll briefly just show all planetary nebula, just to kind of give you a sense of where these guys are. So as you pan around here, you'll recognize some of them, a lot of them you may not recognize, but they're ones that are in the database. And again, as you expect, they're clustered around our sun only because the ones that are further away are too dim to either see or they didn't make my cutoff or something for the magnitudes. And I'll also mention there's making this database was a bit of a chore. You can often get coordinates of where a nebula is, but the distance to it is very often unknown. And for imaging or looking at it through a telescope, that doesn't matter. You don't need to know the distance. You just need to know its coordinates in RA and DEC. But to plot it in the galaxy, of course, you need to know the distance. And because distance to nebulae and planetary nebulae are often very hard to get, particularly for things that are further out, we just don't have a distance to it. So I had to filter all these objects and only choose the ones that we had a known distance to. There'd be a lot more if I didn't have that restriction. Globular clusters, so my favorite. So let's just start with all the globular clusters. And of course, I highlighted M13 because it's my favorite. So this is, again, you hear that they hover around the core of our galaxy like a swarm of bees. And this is it. Pan around, see these guys. And let me also mention at this point, I magnify most of these deep sky objects by a factor. I think these are about 8 times bigger than they really are. Only so because you can't see them otherwise. They become little pinpoints. There actually is a option here under visibility. Visibility to scale the deep sky objects. If I turn that off, that's what they really look like. You can see that. You can see the little pinpricks there. That's how big they really are relative to the galaxy. But that's kind of a boring view. So I have this thing where by default I scale them so you can kind of really see them and get a sense for that. But just remember they are magnified a little bit just so you can observe them in this app. If I pan out, you'll see that man, there are globular clusters way out from our galaxy. And you've heard, and I'm sure most of you know about the Intergalactic Wanderer. If I go here, I think I've got it. I've got it in this. There it is. So this is the NGC 2419 up in the upper left. That's the Intergalactic Wanderer. And again, if you select it, hit info, you can say, oh, it's the distance from Earth is about 270,000 light years away from us. Again, so you can get all the facts and figures here. I also mentioned that as part of the app, I've got the thing on, search the web. So if you don't find the information here you want to, or you want to learn more about it, you can always tap on, just see if this works. So there did a web search for you and brought up. So now you can go and pan and look at that, and you can look at, say, images of the Intergalactic Wanderer and things like that. We'll go back to our app and do that. And of course, it's got its other names for it. There are a bunch of other globular clusters that are pretty far away. So there's the Intergalactic Wanderer we just looked at, but now we've panned out even further. So these things are other globular clusters that are actually part of our galaxy. They're gravitationally bound to our galaxy. Again, these are mostly photographic objects. You're not going to see these in most telescopes. Some of the Palomar objects you can, but a lot of these you really can't detect visually. Let's see, globular cluster, not sure. Yeah, I'm gonna do that. Galaxies. I know imagers love galaxies almost as much as nebulae. So I've got different groupings of galaxies, so you can kind of get a sense of where they are relative to our galaxy and how far away they are. We can just first start with all galaxies, I guess. So now and I should mention, in the upper left corner is the distance that we are located from the sun. So it gives you a sense of kind of how far away we are, looking back on this. So we're pretty far away. We're 92 million light years away from us from this. And I've labeled a lot of the major galaxy groups. So you can see the M83 group over here. I'm sure I can tap M83 without selecting one of the other little galaxies there. The M83 group, the 96 group up the top, upper left, and the 66 group. These are all galaxy groupings that are known. You can look at the local group. So you go back in here and say our local group of galaxies. So now we're in only about 2 million light years away here. Doing that. I have a thing that after you've accessed these views about 20 times, it pops up a rating thing if you haven't rated it yet to give you a chance. I can't rate it because I'm the developer, so it keeps doing this for me. Anyway, so you'll see down here the large Magellanic Cloud, the small Magellanic Cloud, kind of the close ones that you're familiar with probably. That's where they're located. Andromeda Galaxy is over here. So again, it's in relative to us, it's in the southern galactic hemisphere down here. Hercules cluster, again, a lot of these things may not be galaxy, most of these are dwarf galaxies. They're not major galaxies except for Andromeda and the Triangulum Galaxy, which is, of course, over here on the lower left. And again, I can zoom out, pull in a few more things that are considered to be part of our local group. So again, when you're looking at a galaxy, up in the sky, in the same way that you might say, well, what's the distance to it? It's equally informative, or maybe even more informative, to say, well, where is it relative to our galaxy? And so you can, pull up the app, either bring up the Find panel here, and you can search for it, or you can use one of the built-in views to find them and get a sense of where it is you're actually looking when you're imaging or visually observing a particular object. Let's see what galaxy I want to show. I mean, these are just, you sort of saw a lot of these groupings before, the N51 group. Is up there. And again, we're still out at almost 100 million light years away from our sunlight viewpoint. Does anybody have any favorite galaxies? I mean, you can request something if you want, but, or not. But feel free to, if you have a question about some particular object that you've always been curious about, I can show it to you. I also do have the Messier object here. Because those are interesting objects. This is all the Messier objects. Again, most of these ones here in the center are open clusters. You'll see some globular clusters off the plane of the galaxy, like that. If you zoom out, you'll get the Andromeda galaxy down there and its companions. And things like that. So the other thing I wanted to mention here, I'm almost done with my demo of the app, is talk about galactic structure. And this is important enough, I'd like to go through it. So there's 5 main structures that I talk about in the app: the thin disk, the thick disk, the galactic bulge, the stellar halo, and the dark matter halo. So what I'll do, and again, you can, if I tap on the info thing, it'll have some text here you can read about, the thin disk. What I'm going to do actually is show it. And so I kind of do this, highlight that region there with that little kind of wall. So that's the thickness of the thin disk of our galaxy right there. And again, the thin disk is where most star formation stuff happens. And this is going to sound like I'm reading something, because I am. Because I'd like to communicate this information to you. The thin disk region refers to an area about 1,000 light years above and below the plane of the galaxy. The thin disk is where the spiral arms of our galaxy reside, along with young stars, giant molecular clouds, and dust. If you stack 2 CDs on top of each other, this is a good representation of the width to height ratio of the thin disk. The thin disk contains our sun, along with Sirius, Vega, Rigel, Betelgeuse, and Alpha Centauri. It's thought that about 96% of stars near the sun belong to the thin disk. They come in a variety of ages, from freshly formed to over 10 billion years old. The thin disk contains essentially all the galaxy's non-stellar material. The gas and dust are concentrated into an even thinner area than are the stars, with half of the interstellar material being within 80 light years of the galactic plane. This is the area where most new star formation is occurring. Thin disk stars revolve around the galaxy rapidly in mostly circular orbits. Their orbits keep them close to the plane of the galaxy without much of a vertical component to their motion. I'll just stop there on that one and switch over to thick disk. So the thick disk, as the name implies, is substantially thicker than the thin disk. The thick disk of the galaxy was first proposed around 1957, although the idea didn't really take off until the 1980s. As its name implies, it extends further above and below the galactic plane than does the thin disk, being around 7,000 light years in total thickness. Thick disk stars, such as Arcturus, tend to be older and have a lower metallicity than those of the thin disk, with 25% of the sun's metallicity being typical. And let me pause just a second in my reading. Okay. Again, metallicity, for those that don't know, has to do with the ratio of iron to hydrogen atoms in the stars, or in whatever object you're talking about. And so for stars early in the universe's creation, the first stars had no metals at all. They had no heavier elements than hydrogen and helium. And so the metallicity there would be effectively zero. And stuff. And so our sun is the reference point we use. And we say the sun has a metallicity technically it's a log base 10 of this ratio of iron to helium, or excuse me, iron to hydrogen. And it's a log base 10 of that ratio. So actually 0 is our sun's metallicity. Anything that's less than 0 has a lower percentage of metal elements in there. So it turns out like -1 metallicity is 1/10 the amount that the sun has. And 1 metallicity of 1 is 10 times the amount the sun has, again, because it's a log base 10. The formation of the thick disk is still an area of active research. One promising theory has it being formed by the cannibalization of one or more other galaxies, with the newly acquired stars settling into the area of the thick disk. So again, the idea is that our galaxy cannibalized other galaxies nearby. Those star streams got swept into our galaxy, and they're mostly settled into around the disk, but they're above and below the plane of the galaxy, more or less, and their orbits are not circular the way the thin disk stars are. Makes sense? Let's go on to the galactic bulge. The galactic bulge is an ellipsoidal region centered on the galactic core. It's around 2,000 light years across and approximately 12,000 light years thick. The bulge is filled with stars which are both old and they're also metal rich. And that seems like a contradiction because old stars tend not to be high in metals. But it turns out that it's thought that the high concentration of stars in the bulge results in having many generations of stars in a short period of time. So you can build up those metals as stars go supernova or synthesize the heavier elements. Each generation of stars creates more of that stuff. So you can have higher amounts of metals in these stars, even though they're not terribly old when they exist in the galactic core or in the bulge. Since there are few, if any, bulge stars near the sun, relatively little is known about this population of stars. We're still trying to understand it. And then the stellar halo is outlined by that sphere you see on the screen. And I'll just read that little section for you. The stellar halo is a spherical region surrounding the galactic core with a radius of approximately 65,000 light years. The halo contains only very old population 2 stars. So those were early stars that were formed. They are considered among the first stars to have formed in the galaxy. It is also the region containing the majority of the galaxy's globular clusters. The stellar, and again, you probably know from reading that globular clusters contain very old stars. The stellar halo region is free of the gas and dust, so little star formation occurs there. I'm going to stop there on that one and then go to the final one, which is the dark matter halo. So we've zoomed out yet again. We're now, as you see in the upper left, we're about 800,000 light years away from the core of the galaxy here, looking back at it. The dark matter halo is a vast spherical shell surrounding the galaxy and filled with dark matter. Although somewhat speculative, the dark matter halo is deduced by analyzing the motions of dwarf galaxies around the Milky Way. This indicated that most of the mass of the galaxy is beyond the edge of the disk in this spherical shell with a radius of around 300,000 light years. The dark matter is believed to make up about 85% of the mass of the universe. At this time, it's uncertain what dark matter really is. Maybe brown dwarfs, white dwarfs, black holes, or some more exotic form of matter. So that's those are the 5 main structural components of our galaxy. And I think, let me just do this. Let's go back here. Orientation, reset the orientation and turn off. So you can, I've built these views the built-in views. you can construct all these things yourself and then some. So if you go to visibility, right now I've got the dark matter halo shown. If I turn that one off, that disappears. Again, I can say remove all the deep sky objects that are shown there. So now I'm kind of back to a generic beginning view of our galaxy with nothing shown there. I will mention there's a, as you might expect, there's a night vision thing you can use, so you don't blind it out into the night sky. And then there's help that you can do. So some information, again, part of the stuff I presented in the talk, talking about the galactic coordinate system. If you want to refresh yourself on what that is, that's in there. Other things you would expect to be in help. If you want to email me, there's a link there to email me. And if you want to rate our galaxy, give it a 5-star rating, I'd appreciate it. So that's basically the app. So I'm going to turn, does anybody have any questions or anything they want to see before because I'm going to stop screen sharing on my iPad and go back to my presentation. Any questions or anything they want to see?
You mentioned you obtained the coordinates from somewhere else.
From somewhere else? Well, I mostly, so there's something called the SIMBAD database. I use SIMBAD to get most of these coordinates. It depends on the object type. There are the galaxies are something called there's a catalog that a Russian astronomer made for what's called the local volume. And basically the local volume is galaxies out to about 33 million light years, although a few galaxies out to like 80 million light years are in that local volume also. And so I'd use the coordinates that he had there for that. But by and large, the coordinates come from SIMBAD and things. So does that answer your question? Anything else about that?
Yeah.
Okay.
Impressive app.
Thank you. So I will, if there's nothing else anybody wants to see here, I will stop screen sharing. I can figure out how to do that. That there. Go back to Zoom. Stop screen sharing. And then I want to go back to here and start screen sharing on my Mac. I need to go back to my app. Okay, so here we're back from visualizations of our galaxy. So I will mention our galaxy it's a free app. I'm retired. This is my gift to the astronomical community. It's available on Windows, Mac, Linux, iOS, and Android. All you need to do is go to the appropriate place store to get it or download on my site. There is a browser-based version. If you go to ourgalaxy.otherwise.com, it will load that for you. It works just the same way that the apps work, but it runs in a browser. The browser-based thing is only for desktop machines. It really doesn't run well on mobile machines. I will mention I wrote this app using the Unity game engine to do all the 3D stuff, and the Unity game engine doesn't work well on some mobile devices, at least for the kind of stuff I'm trying to do. So that's why it doesn't. It's really a desktop thing for the browser based. So if you're interested and want to try this thing, you can go to www.otherwise.com, my website. It'll have details about the app, and it will have download links. Some of the links go to the App Store. So of course, to download for iOS, you got to go to the Apple App Store. Likewise for the Mac, it's on the Mac App Store. Windows, it's available on the Windows Store, although you can. I do have a link there to just download the executable directly if you don't want to deal with the Windows App Store, which I know some people hate. And there's a Linux version also, and an Android version. So hopefully everybody, I will mention, I originally wrote this app for only for iOS and Mac OS. So it was Apple products. And I wrote that using a very different technology than the Unity game framework. People liked it a lot. And of course, where's the Windows version? Where's the Android version? So finally I broke down and rewrote the app, spent 9 months rewriting it in this cross-platform framework. And that's what's available today. So I mentioned I was going to talk about Plato's cave allegory. I'm sure many of you have heard of this before. His allegory of the cave. So Plato described a world where there were these prisoners that were chained up. My cursor back on point things. They're the prisoners down here. They were chained to a wall. Their heads were fixed so they could only look forward. And what they could see, though, on the wall facing them, there was light coming from a fire over here, and all their keepers would be moving around up here, and they could see their shadows up on this wall. And it was a flat two-dimensional wall. And that became the prisoner's reality. They thought the world is this two-dimensional thing. And that's what I see, and that's all I know. And then finally, but at one point, some prisoner broke loose and he got away. And here he is escaping out. And he escaped out into the ascent to the sunlight here. And he said, oh my God, the world isn't two-dimensional, it's three-dimensional. And there's this whole other, it's this whole other thing I never knew existed. And I think this is very apt for what I'm trying to do with our galaxy. Most of us are familiar with star charts and where things are in the night sky. And it's a 2D representation. We see it on the celestial sphere. And you say, well, where is it three-dimensionally in the galaxy or around the galaxy? And say, I don't know. I've never seen that before. And so in the same way the prisoner escaped the cave here and realized the three-dimensional view, I'm hoping that the Our Galaxy app helps people break out from just thinking two-dimensionally and RA deck, and they add that distance dimension. And with that and a little bit of trigonometry, you can figure out where things are actually in the galaxy. Conclusions. Not a lot of conclusions. I hope I've motivated you guys to realize that there's some benefit in thinking in 3D. I'm actually very surprised by the relative lack of interest in the app. It's not talked about. People don't seem to use it. A lot of people have downloaded it and a lot of people do use it. But in like the Cloudy Nights forums, it's rarely talked about. People don't look at it and learn new stuff about it that at least I can detect. But there's a lot of benefit in understanding this in the same way that people like to look up the distance to an object, and it's just this it's a neat thing to know. How far away is that object from us? Well, in the same way, I think it's really beneficial, or at least interesting, to know where it is three-dimensionally. And it really will enhance your observing, probably enhance your imaging, just to have this sense of where these objects are. I also find I do a lot of public outreach. That's one of my favorite aspects of the hobby, actually. And I use this app at public outreach all the time. And of course, people always say, well, how far away is that thing we're looking at? And I'll tell them, and I'll say, well, here's where it actually is in the galaxy that you're looking at. And they're blown away. They think it's just really, really cool to be able to see this representation of where it is they're looking in the galaxy when they're looking at a globular cluster, an open cluster, nebulae, things like that, or some other galaxy. And then there's this question, well, why has this been neglected for so long? I don't fully understand. I don't understand what professional astronomers know. I mean, maybe they think about this stuff in 3 dimensions all the time, or maybe not. But I can guarantee you from talking to amateurs, most amateur astronomers just don't think this way. And it's kind of a mystery to me. And again, until I read Craig Crossan's book, that binocular astronomy book, I didn't understand this stuff. And yes, it's mentioned in magazine articles and websites and things like that. They might mention a little bit about it, but they really don't have a good visualization tool to see it. And there are a few websites that that try to do it, but it's more of a static kind of view. It's not something you can kind of pan around and zoom in and out and see it. So again, I will say that it still mystifies me a little bit why what I consider to be a revolutionary way of looking at things doesn't catch on more. So, you know, if you guys use this thing, download it. Again, it's a free app, doesn't cost you anything. Matter of fact, if you go to the ourgalaxy.otherwise.com, you don't even have to download anything. You just go to the website. You can play with it a little bit. If you find it exciting and think it's, you know, cool, I would appreciate it very much if you would spread the word, tell other people about it, and maybe generate more interest in it and things like that. I will mention that a lot of the information about the structure of our galaxy comes from a book called The Alchemy of the Heavens by Ken Croswell. This is it's getting a little dated now. I forget when it was written. It was written in the early, I don't know, 2004 or something like that. It's becoming a little dated now, but he does a really, really good job of talking about, you know, our galaxy, what's going on in our galaxy and things like that. And I highly recommend, if you guys have any interest in this, to seek out this book and read it. It really is quite good. Again, my website is www.otherwise.com. If you want to email me, it's just bill@otherwise.com. And that is it. I'm going to stop screen sharing.
Thank you very much, Bill.
Yeah.
That was terrific. So please, it's time for questions for Bill. Give it a second. And does anybody have any follow-up questions or questions about his talk? All right, I'll get things started. Oh, there is a question.
What is the motivation for the name? The name of the app, Our Galaxy. Is there more to that? I see. Oh, name Otherwise. So I founded Otherwise back 1990, and I wanted to do something. And again, my history. I actually worked for. Let me briefly mention my history. I'm actually trained as a zoologist. I'm not a programmer by training. I've had like one computer programming course. I'm kind of self-taught. But I actually am interested in theoretical population dynamics and ecosystem modeling and things like that. And that's how I got my initial experience with computers and things. I left academics to start a software company. I was up in Washington State in Seattle at the time. We founded a company. We wrote software for, we started to write a word processor for Macintosh. And so Mac came out in '84. A couple years before that, Apple approached us and wanted us to write a word processor for the Macintosh. We actually wrote Write Now, if anybody is familiar with Write Now. And that's another app I've written way back when, in the dark ages. And then when Steve Jobs got kicked out of Next Computers, I got kicked out of Apple and founded Next Computers, they needed programmers and they needed somebody to write a word processor. And I said, well, how about those guys up in Seattle? They did Right Now, and that worked out pretty well. And so they actually bought our company and hired us. And I went down and worked in the Bay Area for about 4 years, working with Steve and stuff. And I was employee 18 there. So, you know, had fairly regular interaction with him and things like that. And then I decided to leave. I got tired of the Bay Area and wanted to get back up to Washington State. And when I was going to form a company up there, I was looking around for names, and it's been a long story here. I just wanted to do some software that was a little different. It was not, you know, the run-of-the-mill thing. And so I thought, well, let's call my company Otherwise. And again, because I registered this domain back in 1990, before all the good domains were snapped up, that was totally available, and I got the name Otherwise. And I've been using the name Otherwise for, you know, 32 years now or so. Anyway, that's my question is it open source? No, it's not open source. It is totally closed source. Sorry about that. What it is, I guess I could consider open sourcing it, but I'm not sure that's what I want to do. Thank you, I appreciate that. Can we contribute to code? No, it's not open source. What's the cross-platform technology used? As I mentioned, it's the Unity game engine. Unity game engine is something totally different than what I was familiar with before. And it's a totally different way of writing apps. And so there was definitely a learning curve for me to do that. In reality, I actually started out with a different cross-platform thing called Xamarin. But Xamarin had so many bugs and it was so frustrating. I finally just gave up on it. It's like, I can't make this work in Xamarin. That's when I went over and tried Unity, and Unity actually works pretty well, but I'd say it's very different than most of the programming I've done. Any other questions?
Let me ask one. So it seems like, well, the one thing that struck me when you were showing, like the stars was obviously, like you said, since you were limited to the, magnitude 6 or whatever, it was going to be nearby stars. So
right.
And you mentioned that you needed to limit the number of stars for I guess display reasons. But it seems like it's screaming for, why not show?
Well, I could.
They have like a few 100 million stars, right? And so maybe you can do animations with them, but you could probably have.
I don't think you can do a real-time animation with that many, anywhere near that many stars.
Right.
The app would just bog down and just become unusable. Yes, you do see you'll see videos of animations with many, many more stars, but those are not real time. Those are things that, it's like Pixar. They have render engines that go off and crank for 2 days to generate that video. And no, I'm sure I could, triple, quadruple the number of stars and have no real problem.
But what about like, okay, so for certain views are not animations, like just here's a top down or a face on view of the galaxy, things like that, limited views, because from a educational or scientific point of view, it's not the case that all the stars are gathered, on our arm right near us, right? They're distributed around. And
although there's definitely there's a sampling problem that, if you showed, dimmer stars or further stars and things there, there's a lot of stars that, we understand our neighborhood of the sun pretty well and what stars are there. As you get further out, in the next spiral arm outward even, and maybe with the Gaia data, it's changing for sure, but we don't have nearly a thorough sampling of the stars there. There's just stuff that's too obscured by dust and whatnot, so that it kind of might give a wrong impression. Again, you'll still see this thing where, hey, it still looks like things are clustered around our sun, and that's only because it's not because the stars aren't out there. It's because they're so obscured that even with Gaia, we don't have good information on them. Gaia does have a lot more stars, but it's not a uniform representation. So I don't know. You're right, and I've thought about doing this. Nobody has asked for it. It would be a lot of work too, and it would also you could probably run it on desktop machines with a lot more stars. Again, one of my goals was to have this run on mobile devices, so you could carry it out under the night sky and use it for outreach and things like that. And there, they're fast enough now, but it's more memory. Each star, has a bunch of data associated with it. Each one takes up memory, and if you load it into memory, and most of it has to be resident in memory, so that as you pan around, you see things and whatnot. So that's a big memory load, and I'm not sure mobile devices can handle that.
Okay, thanks.
This is very satisfying. My brain likes to know where I am and where things are in relationship. I like binocular viewing for 3D effect too. Thank you very much. Well, thank you. Thanks for the presentation. Okay. All right. Well, I've enjoyed talking to you guys. I hope I've at least nudged you and excited you enough that you might go try the app and see what it does. Again, I'll mention that if you bought the app, or if you got the app off an app store, where you can rate the app, and you're so inclined, ratings are gold for developers. Again, I don't sell this app, so I'm going to make any money, but I'd like to see it get spread, and the more positive ratings. And like fortunately, on the Apple Store, I've got a 4.8 out of 5 rating on it, so people like it. But I would be happy to have you guys rate it if you're so inclined. I'll also ask a question. I see Susan Warden on here. I used to know a Susan Warden once upon a time. I'm trying to remember which company I worked for at the time. Susan Warden, are you familiar with me at all? Does my name sound familiar?
No, it doesn't, but I loved your presentation. Thank you so much, and I've already downloaded the app.
Okay, well, it must be another Susan Warden someplace.
It's a common name.
It's a common name? Okay, well, that must explain it then.
All right.
Are we done?
Well, it sounds like, last chance for questions, but it sounds like we're probably done. So unless we hear a question in the next few seconds, why doesn't everybody unmute and applaud or thank?
I have a question.
Go ahead.
Yes, we have a question from Monica?
It's
Mona?
Yeah, my question is, I wasn't paying attention the whole time. Will this be available? I know you're recording. Will it be available on YouTube?
Yes, we email to our mailing list and, the YouTube link. And so it should be available like all our other talks. So no problem. You get the emails from the SJAA imaging mailing list?
Yes, but I have to admit, I'm not loyal. I'm kind of a busy grandma.
Okay, well, anyway,
I usually post them in the meetup too, the recording link. Yeah, in the comments for this meetup.
Thank you.
I will post it when it's up on YouTube.
Great.
All right.
Okay, guys.
Well, everybody
enjoyed it. Thanks so much.
Thank you.
Thanks, Bill.
Thank you.
Thank you.
Thank you.
All right, you guys have a good rest of your week.
Okay, should we do the set?